So now in particular, let's talk about the ligand substitution reaction, where we take one of the ligands L from the metal center and we replace it with a new ligand L prime. Let's first talk about, from organic chemistry, this is a reaction coordinate diagram. We have reactants. The reactants flow over a transition state. If you're on the top of the hill, there's a small valley. It's an intermediate. We follow over a second transition state down to products. Two distances of note here are the energy from the reactants up to this transition state. That's the free energy of activation. We'll call that delta G double dagger. And from the reactants to the products, this is the free energy of reaction. So we're going to talk about two different main reaction pathways, a dissociative and an associative reaction pathway. Both of these are two-step pathways and they involve an intermediate. We're either going to remove ligand X from the metal center and replace it with ligand Y, or we're going to first add ligand Y to the metal center and then remove ligand X. So let's look at this dissociative pathway first. We take this complex, we first remove ligand X, leaving a lower coordination number intermediate, and now we have free X. Now this lower coordination number intermediate can pick up Y, and overall what we've done is we've removed X and we've added Y. So X has been replaced by Y in a dissociative mechanism. We removed X and added Y. Alternatively, we can take the complex, we can add Y. Now we have a higher coordination number intermediate. Okay, if this was 6 coordinate, for example, now this would be a 7 coordinate intermediate. Now this complex, which tends to be not stable, loses X, and so we've taken this complex with X and we've replaced X with Y. Note that in both mechanisms, overall what has happened is X has been replaced with Y, X has been replaced with Y, but they follow two very different pathways, either first losing X and then gaining Y, or first gaining Y, then losing X. So yeah, notice that we can't tell anything from the products. We're going to have to look for another way to determine what the mechanism was here. You may want to review a similar thing that can happen in organic chemistry. We have two different ways to replace, say, a halide with a hydroxide ion. So OH minus reacts here with methyl chloride. We go over a transition state and we form methanol and chloride. So hydroxide, methyl chloride, methanol, and chloride. Going over a transition state, not forming any intermediate species. This is our classic SN2 reaction. Alternatively here, we have tert-butyl bromide reacting with hydroxide. Well, it ends up in this reaction. It's a lower energy path to first undergo cleavage of the carbon-bromine bond. So we go over a transition state. We form a carbocation intermediate now. We have an intermediate here in the middle. We have a carbocation, and hydroxide hasn't done anything yet, and bromide is free. Well, the carbocation and the hydroxide can go over a transition state and form tert-butyl alcohol, tert-butanol, and bromide. This is a two-step process with an intermediate here in the middle. And this is a good analogy to our dissociative mechanism. It ends up that SN2 is not a good model for our associative. We'll see one here on the next slide that is. SN1 is really a good model for our dissociative, where we break a bond and then make a bond. A better model from organic chemistry for our associative mechanism is an acyl chloride here reacting with sodium methoxide. Sodium methoxide, the oxygen of the methoxide attacks the carbonyl, and we get a tetrahedral intermediate going over first a large transition state. The tetrahedral intermediate then goes over a smaller transition state to form the ester and free chloride. So here we start with two reactants. We go over, form an intermediate, and then this intermediate collapses to a more stable product. All right, so back to the inorganic mechanism. So here we have a specific case. We were very general before. We have ML5X, which I've drawn as an octahedral complex. The slow step is MX cleavage. And then we can form one of two intermediates. And I'm not going to spend time. If you want to think about them yourself, you can. But these would be the two sort of extreme intermediates that could form. And then ML5 reacts with Y to form ML5Y. So overall, we've taken and we've replaced this X ligand with a Y ligand. The important thing for this is now we actually have a handle on this extreme case. Because the first step is slow and the second step is fast, the kinetics of the reaction are dominated by the first step. We go through and do simplifications for this. It ends up that the rate is equal to some rate constant, K1, times the concentration of the starting ML5X species. Okay, and it has no dependence on the concentration of the incoming ligand Y. All right, let's look at the other case. We have our octahedral ML5X species. It reacts with Y to form an ML5XY species. Again, don't worry too much about these are two extreme cases of what that could actually look like. ML5XY then undergoes a fast step to lose X. So the slow step is picking up Y, the fast step is losing X. Since this slow step is what determines the kinetics, both the concentration of ML5X and Y are important, and so the rate is equal to a rate constant times the concentration of the metal complex times the concentration of the incoming ligand. Contrast that with the dissociative mechanism, which only the concentration of the starting metal complex matters. So we have a dissociative reaction mechanism that we've talked about, an associative reaction mechanism that we've talked about. There's also something that's right in the middle, and it's interchange. So the interchange, in the dissociative, we lost X and then gained Y. In the associative, we gained Y and then lost X. Interchange is directly in the middle where we are precisely gaining the Y as we're losing the X. So you can think of Y coming in, and as it comes in, it pushes X out. And what do each of these look like? So the dissociative looks like the SN1 reaction from organic chemistry. The associative looks a lot like an addition-elimination reaction from organic chemistry. And we finally got back to SN2. The SN2 looks like, the interchange looks like the SN2 from organic chemistry, where the MX bond is breaking precisely as the MY bond is forming. All right, so we end up having a spectrum of what can happen here. We have the associative reaction mechanism, where the new bond, the MY bond, is 100% completely made before the MX bond is broken. I've grayed out these. I'll mention these after I get to 3. So here, 3, interchange. The MX bond is breaking and the MY bond are forming simultaneously. So the MX bond is exactly half broken and the MY bond is exactly half formed in a perfect interchange reaction. Associative interchange is between the two. Skip over 4 there, and we'll go back and hit it in a second. Dissociative, the MX bond is 100% broken before the MY bond starts to form, and the dissociative interchange would be somewhere in between. So 2 and 4 are not important for you guys to know, other than to know this is what happens if they lie in between those. In between, for example, associative and interchange is an associative interchange, and in between interchange and dissociative is dissociative interchange. All right, to summarize, principal mechanisms of ligand exchange in octahedral complexes. We start with an ML5X. The slow step is breaking the MX bond. The fast step is adding the new ligand, and so the kinetics depend exclusively on the concentration of the starting ML5X complex. Whereas associative, the slow step is addition of Y. Therefore, the concentration of both the starting complex and the identity of the Y ligand matter. And so this is the slow step. The second step is fast. So it's this first slow step that determines the kinetics. And the big idea here is to compare the two. The concentration of Y matters for associative. It doesn't matter for dissociative. Ideally, for a 100% associative reaction, this would be Y to the first power. All right, and then here's all three. We have our pure dissociative mechanism, where we go over a transition state. We form an intermediate where we have ML5. We have the X ligand by itself floating around in solution. We have the Y ligand by itself, neither attached at all to the metal. And then Y swoops in, attacks, and we form the ML5Y complex plus free X. The pure associative, we go over a transition state. We form a complex where we have increased the coordination number. So this would be like ML5XY. That then goes over a transition state to break the MX bond. And then pure interchange looks like an SN2. So the bonds are exactly half formed. So MX is half broken and MY is half formed. And so you can think about this as the Y ligand coming in and pushing out the X ligand.